we talk about transmission lines, it's usually pretty complicated to determine a whole bunch of different parameters of the transmission line at different points along the line. So what we use is this thing called the Smith chart now. So the Smith chart is essentially a tool that relates the impedance of the line to the reflection coefficient of the line. And now this reflection coefficient and this impedance will vary at different points along the line. And therefore we're able to plot these values along the line, and we're able to understand how the impedance and the reflection coefficient of this line varies as a function of the distance along the line. So before we get into the actual, dealing with the specifics of how the Smith chart works and how to actually use it for solving specific questions, we'll take a look at a little bit of the background and some important points of interest of the actual Smith chart. So we'll start with a little bit of background theory. And we'll talk about how this, this really what looks to be a very complicated plot or set of graphs, where it actually comes from, and the basis for this kind of plot and where we can start. So if you recall, we have gamma L, it's going to be ZL minus Z naught over ZL plus Z naught. Now this is a very standard expression for reflection coefficient. This applies in electromagnetic theory as well. And so in transmission lines, it's a sort of analogous expression. And also we have that in general, some value Z impedance will be equal to 1 plus the reflection coefficient over 1 minus the reflection coefficient. And in general, we have gamma is going to be magnitude of gamma e to the j theta gamma, or in other words, it's going to have a real component and it's going to have a imaginary component. So in general, the reflection coefficient is complex. Okay, so on the Smith chart, it's important to notice that all parameters are normalized. Now, what does that mean? That means that we can use the exact same Smith chart for any other line that we want. So it doesn't matter if my characteristic impedance is 100, if it's 50, if it's 200, if it's 500. I can just normalize the impedance and I will be able to use a single chart for any line that I have. So all parameters are normalized on Smith charts. And so before we can actually solve the questions, what we usually do is take the characteristic impedance of the line and we divide any impedance by that characteristic impedance. And so that way we can get everything in terms of the characteristic impedance of that given line. So let's take a look at this normalized impedance, or the concept of this normalized impedance. And we'll call it, we'll just call it ZL, and we'll give it a bar, okay? And the bar should not be mistaken with a vector sign. This is a bar to signify that it's normalized. You can use a lowercase, but it's really just a matter of sign convention. So I take ZL and I divide it by Z naught. And in general, I'll have some value R plus JX. And R is going to be the normalized resistance and X is the normalized reactance, because in general, I know that these lines can have complex impedances. And loads can be complex, and so we deal with these things in general terms. Now what can we do? We can go ahead and let's sub ZL bar into the equation for gamma L, okay? So what happens then? We get, if you recall, just above here, we have gamma L equals gamma R plus J gamma I. And this is going to be this normalized thing divided by this normalized thing here. Should probably give a little separation there so you can actually tell the difference. Okay. And so this is essentially just you divide the thing by Z naught and then you can factor it out and you can actually get this expression relatively simple. Another way we can actually do this is if we go ahead and rearrange this equation. What we can do is we can solve in terms of ZL bar, which we say is r plus jx, if you recall, further up. So what I'm going to do is I'm going to rewrite this expression here, and I'm just going to flip it around pretty much, and I want to get all the gammas on the right side, and I want to get all the z's on the left side. So what I will be left with, in this case, is I'll have a 1 plus gamma r plus j gamma I over 1 minus gamma r minus j gamma I. Okay, so now I have ZL in terms of the reflection coefficients. And now what we can do is we can actually compare this with this expression that I have here. So what I'm going to do is I'll rewrite on this side. If you just look at the line above here, actually, this is equal to j gamma I. Okay. So now, as a result, what happens is, if I take the magnitude, or I'll take the real and imaginary parts, let's say. I'll take the real and imaginary parts of this expression here, and I'll equate them with R and X. So essentially, I'll have an expression for the normalized resistance, and I'll have an expression for the normalized reactance. What would these expressions actually look like if I actually take the real part of this ZL bar equation that I have, and I take the imaginary parts and I equate them with R, I will be left with the following equations. So I'll have gamma R squared minus gamma I squared divided by 1 plus gamma R squared minus 2 gamma R plus gamma I squared. So that's for R. And for X, I will have 2 gamma I divided by 1 plus gamma R squared minus 2 gamma R plus gamma I squared. Now if I take both of these equations and I do a little bit of rearranging and I make some, it's essentially just a manipulation. So what I want to do is I want to get these into some form that I'm familiar with. So if I rearrange R and X, what I will get is I can get this equation right here over R plus 1 squared plus gamma I squared is going to be 1 over 1 plus R squared. So this is the equation for R. And similarly, I can find an equation for X. What I will get is I'll get gamma R minus 1 squared plus gamma I minus 1 over X squared. And this is going to be equal to 1 over X. So now if you realize, sorry, this last term should be squared as well. So now if we look at this, you may remember from grade 11 or some high school level mathematics that the equation of a circle is actually in the form x squared plus y squared equals r squared. Now if you look at these expressions we have here, these are essentially the equations of a circle. And so what do we have? We have that this first one here is the equation of a circle in the plane that is defined by gamma r and gamma I, with a circle that is going to have a center, of course, that will be offset based on this equation. So it's going to be centered at the value of r over r plus 1 and 0, and it's going to have a radius of that term on the right side of the equal sign, 1 over 1 plus r. So that's what this first equation tells me. Now what does this second equation tell me? This is also the equation of a circle, which is also in that same plane, but the values are a little different, you know. So this is going to be centered at centered at what? 1 and 1 over x, and it's going to have a radius of what? 1 over x. So here we have it. These are the equations for two different circles. So now the thing about this Smith chart is essentially what it is. It's you're taking these circles and you superimpose these circles onto one another, and you end up with the Smith chart. So if you look at the Smith chart carefully, you'll notice it's a bunch of circles everywhere. Where do these circles come from? It comes from these equations essentially. And so these circles that we see on the Smith chart are really just substituting certain values into this thing and finding different circles, and you can actually give them some meaning after. So some things to note here about this about these equations. We have R is always positive because we know that resistance is always going to have to be positive, at least in these conventional cases. We have what? X can be positive or negative. X can be any sort of number, and so if it's positive, then it's what? This is going to be inductive reactance, or it can be negative, and if it's negative, then it's what? It's capacitive reactance. So we have here the general case for the impedance. So now if we superimpose these circles, like I said, we can actually get the Smith chart. So, I mean, for example, if you think about, I don't know, if we have, let's say, Z equals 2 plus J. What is this? This is going to be the point where the R equals 2 and X equals 1 circles intersect, right? So you'll have to find those two circles on the Smith chart. You'll find where the 2 points intersect, and you'll draw a dot there. So there are actually other things that we can use the Smith chart for as well, besides just R and X circles. So we have what's called the S circle. So what is the S circle? Maybe we should give this a little bit of a highlight here just so we can actually distinguish it from the rest. So we have this S circle. Now this S circle is actually the SWR circle. It's also known as sometimes. So, well, I guess more specifically, it's called the constant SWR circle. So the SWR along anywhere on this circle will be constant. So that's another thing we can use it for. So you'll have the R circles, you'll have the X circles, you'll have the S circles, and these things are usually centered, well, not usually, they are centered at the origin. Okay, and they can vary from whatever values that the SWR varies from. It varies from, if anybody knows, would be 1 to infinity. Okay, so how do we find the SWR? So if we have this S circle, to find the SWR of the actual line that we're dealing with, what we have to do is locate the point where the S circle intersects the real axis. So the gamma R axis, which will be the, I guess you can say, horizontal axis, or what's considered the x-axis in a Cartesian coordinate system. So these S circles, since we can relate S to the magnitude of gamma, sometimes these are called the magnitude, or these are also called gamma circles, but generally we'll call them S circles. It's a little more definitive than the gamma circles. So now we have some points of interest along this Smith chart. And these are essentially things that we should know, which are sort of inherent to the properties of the Smith chart, and you won't really know unless you know them. So we have this point where it's called the short circuit point, and at this point x equals 0 and r equals 0. Okay, so ZL is going to equal 0 plus J0. What does this mean? That means PSC is actually going to be a short circuit on the line. Is a short circuit on the line. Now there might not physically be a short circuit, but what that means is if you are looking at that point on the line, that the whatever parameters you're looking at from that point, the circuit will appear as, or the line will appear like a short circuit. Okay, and so this is the leftmost point. So if you go to the entire Smith chart, go to the leftmost point of the Smith chart along the outside, that is PSC. Okay, so if we have PSC, one would assume that we also have a POC. Now at this point, x equals infinity and r equals infinity. So ZL equals, surprise, surprise, infinity plus infinity. Now, POC is also considered a short. I mean, sometimes they call it an open circuit, but I mean, I believe in terms of the actual Smith chart, when you're talking about the Smith chart, they just call both of them short circuit points, simply for, I believe there's something about a historical reason as to why they do that. But in any case, we call POC and PSC short circuits. So the thing about POC though is it's on the other side. So POC is actually is the rightmost point. So we'll say rightmost point. Okay, cool. So we have these two properties. What else do we have? Let's talk about the actual size of the thing. So one revolution around the Smith chart, I'll just call it the SC for abbreviating, is actually equal to lambda over 2 on the transmission line. So if I do one whole revolution around the Smith chart and I come back to the point where I'm standing, or where I was when I left, I've traveled lambda over 2 along the transmission line, okay? Cool. What else do we have? We have that if I go clockwise along the Smith chart, this is going to be towards the generator or away from the load. If I go counter clockwise, then this is actually towards the load. So wherever, at any given point, wherever I'm standing, I can either go one direction or I can go in the other direction, unless I'm already at the load and I can't go any further. Physically, it doesn't make any sense to go any further. There's also three scales you'll notice on the Smith chart. You can use really whichever one you want. Two are actually in terms of the wavelength. One of them is in terms of degrees. So it's really just a matter of preference, I guess. The degrees scale is useful when you're finding angles associated with the complex reflection coefficient and all that. But the other ones are in terms of wavelengths. So it's really just a matter of preference at that point, whichever one you want to use. So we have some properties of voltages. So we have a voltage Vmax occurs when Zin is a max. Okay, and so this point we can actually consider is going to actually be along the positive gamma r axis at the point 0 POC. So whenever I'm at 0 POC, I am at Vmax. This is the maximum along the line. Okay, so likewise we would have a point that is the voltage Vmin along the line somewhere. So this one occurs when Zin is a minimum. So where is it a minimum? I mean, if one is POC, one would imagine that the other one would be at PSC. So this is going to be at the negative gamma R axis. So this is going to be at 0 and PSC. And you should also note that every Vmax and Vmin are lambda over 4 apart. Now we know this from basic electromagnetic theory as well, when we said that adjacent minimums or maximum values are at lambda over 2, therefore every adjacent maximum and minimum would be at lambda over 4. So another couple of things, what else do we have? We have the Smith chart can be used for impedance or admittance, if I'm doing it in terms of admittance. So we can use what we can call the admittance chart. You'll have a y equals g plus jb, and so g and b are essentially the same thing as r and x in terms of the circles. But at the end of the day, what you have to realize is you're actually calculating admittance and not impedance, so you'll have to convert back after at any given point. So what are the parameters we can find? We can use the Smith chart to find a whole bunch of things, really. So we can find gamma, we can find S, we can find Zn, or in other words, Yn, depending on whichever one we're in. We can find the location of Vmax and Vmin if we know Z0, ZL, lambda, and the line length. So we can pretty much find a whole bunch of different things just given, a relatively simple setup and a relatively simple configuration. Gaining some experience with the actual Smith chart, we can use it to find a whole bunch of things. So it's actually funny, the guy who invented this thing, it was in the 30s. His name was Philip Smith, Philip H. Smith to be precise. And he actually called this thing the transmission line calculator when he wrote the paper. And so if you actually read the paper, he calls it a transmission line calculator, which is essentially exactly what it is. So I hope you found this video useful. If you haven't already, subscribe to the channel so you can actually get updates when I upload a new video. There will be videos uploaded in the future for actually dealing with the Smith chart in terms of questions, specific line questions. And other than that, we will see you in the next one.